Hausberg equation only works for the buffer system because you have a larger amount. That means your change is much smaller than your initial, and that's why you see the initial here, right? Because you assume the initial concentration is the same as your equilibrium. Right? So basically, when you apply the ice chart for a buffer system, our approximation always valid. Okay, so that is how to explain the Hansen-Hausberg equation. And we did some example to use Hansen-Hausberg equation, right? So now, let's do one more example. Still related with the application for Hansen-Hausberg equation, but in another way. So here tells you, okay, you already know what kind of buffer you want. You want to prepare this buffer, okay, acetic acid. And you're given the pH, pH is given. I want the pH 5.44, I need that pH. And also the pKa is given. It asks you what is the ratio of the conjugate base, right? And the weak acid. What is the ratio you need? So think about that. When you say buffer and some calculation, right? You first see in your mind, okay, if I have a buffer, I should consider Hansen-Hausberg equation first. If it doesn't work, then I consider other things. Let's see, okay, I'm having pH, having pKa. So the relationship between pH and pKa is the Hansen-Hausberg equation. Log base, here is conjugate base, acetate on. Right? And then the acid is my acetic acid. So now, you just say what is the given, what is unknown. So pH, okay, good, it's given. pKa, given. It asks you the ratio. Through this equation, you cannot directly get the ratio, but you can get a log with this ratio, right? So let's say. So 5.44 equal to 4.74 plus this log. So now just solve this log. So I got it 4. So minus 4.74 on both sides, or you move to the left, become a negative. So you can solve it. So that is log this ratio. So then what is the ratio? What is this whole number here? Negative or positive? So now it's positive because we don't have a negative side here, right? So that's actually a good point. Be careful. Here is a plus. If it's pH, then it's negative, right? But here is a plus, so it's positive. Okay. So log this number equal to 0.7. So this number is equal to 0.2 positive. Okay? So when you have a problem, make sure you check the sign. So here is the 0.2 positive. Good. So now you can use your calculator to get it. 5. 5. 5.01, right? So be careful. If you got a question in your test, ask you the ratio. If you get 7.9, 2.5, 2.8, it's totally fine. Don't have to be a whole number. Okay? So it's any number, whatever number you get. And if in the test you say, okay, the answer A, B, C, D doesn't have this answer, but one answer said is 5. So then it's 5. Pick the closest. Okay, so pick the closest. So that is another way how to apply the Henderson-House equation. You're given pH and you're given pKa, ask you the ratio of the concentration, right? You just do a conversion for the Henderson-House equation. Actually, we use this type of problem a lot in a lab, right? Because you know what buffer you want. Okay, I want to prepare a buffer with pH like 5. So first see which acid should I pick, which conjugate base should I pick. Then how to determine the amount, right? So you need to find the pKa from online, and then determine the ratio, and then say, for example, you want to get 1 liter, so how much you should pick, right? So that actually used a lot in a real lab, okay? So any question about this problem? So still Henderson-House equation. So now related with that, the ratio. We are talking about the buffer capacity or the buffer pH range. So how can I know the buffer is good? How can I know if I want to prepare the buffer with pH 5.44? Which chemicals should I pick? Which acid should I pick? And then which conjugate base should I pick? Right? So that depends on the buffer capacity. Buffer capacity tells you how to make a good buffer, how to select the correct chemicals for the desired pH. If you already know what pH you want for the buffer, so which chemical you should pick actually depends on the pKa of that chemical, right? The pKa. So always say the buffer capacity and the buffer pH range basically tells you how to make a good buffer and how to make a good buffer. Large amount for sure, you must have a large amount. And then you have a weak seed. That makes you a buffer. How can I know it's a good buffer? So first thing is, if you want to make a good buffer, it must be large amount, right? So with large amount. And you already know from the definition, large amount of weak acid plus its conjugate base, which is also weak base, conjugate base. Here, conjugate base. There must be a weak acid plus its conjugate base. Or, of course, it can be weak base, large amount, or large amount of weak base plus conjugate acid. Right? Depends on what pH you want. So that is through the definition we know. To make a good buffer, to make it most effective, you must have a large amount. Right? Large amount. And another thing related is the pKa. In order to make a good buffer, you should have when the concentration of weak acid equal to its conjugate base. This way, conjugate base. And of course, or the concentration of weak base equal to conjugate acid. Very important. So through the Harrison-Hausbach equation, we know when the concentration of acid equal to base, no matter weak acid conjugate base or weak base conjugate acid, what happened to pH? If the concentration of these two equal to each other, what happened to pH at pK? Become, if here, right? If A over A equal to 1, what happened to pH? So log equal to 0. So what happened to pH? Equal to pKa, right? Because plus a 0. Okay? So when the concentration of your acid and base are equal, so your log becomes 0. So the Harrison-Hausbach equation, your pH equal to 0. Okay? So that is most effective. And that is why when you do the titration in 1211 to determine pKa, remember you process data at half equivalent point, right? You get pH equal to pKa. That is the most effective buffer when the concentration of acid equal to base or base equal to acid. So the pH equal to pKa. That is most effective buffer. So we are talking about most effective, right? But sometimes you don't have to reach the most effective. You just make sure it's effective. You don't have to be a perfect buffer. It's just a good buffer. So we have the effect pH range, not most effect. The effect pH range is when the buffer have a pH larger than pKa minus 1 or smaller than pKa plus 1. If you have concentration related, then it will be concentration of proton plus or minus. Means if you take log on both sides, right? So that will be Ka times 10. I mean Ka divided by 10 and Ka times 10. And so that is for the concentration range. But here, since we are talking about pH, so you know pKa.
Charge your phone 3 times. Merry Christmas.
If you want, I can write more, right? So or it means concentration of photon is larger than Ka divided by 10, smaller than Ka times 10. Right? So the same thing. Just take log on both sides. Negative on both sides. So that is effective pH range or the concentration of hydronium ion. Because in biochem, you may need to do some conversion for this too. So, but for our class, so the pH thing, if you understand, that's enough. Okay? So pH have this range, plus minus basically pKa plus minus 1. Okay? So why we define minus 1 plus 1? That's through the experimental data. Okay? So for example, so we'll give you some example later. So any question here before we go through the examples? Okay. So the examples actually I picked from your worksheet. Somebody may already work on that. So be careful, most effective and effective. Effective is a range. Most effective is just that point. Okay? So be careful how the question asks you. If I ask you most effective, only when your pH equals to pKa. If I ask you effective range, then it's a range. Okay? So now let's see some example. That is very useful in the lab, right? Determining which chemical you should pick to make a special buffer. So which of these following acids would be best choice to combine with its sodium salt? Basically means conjugate base, right? So acid here means conjugate base, salt. The salt comes from the acid to make conjugate base. To make a buffer to mimic human blood, and the pH for human blood is about 0.35 to 0.45. So I put the 7.55 here. Ask you why. You try to work by yourself. Pick one. Gives you the pKa's. Asking you to make the buffer with this pH. What is the range? How to make an effective buffer? If I give you pH larger so you basically need to find out which pKa is in this range. Can make this pH. So pH now is no, right? Larger than number, smaller than number. Let's say one by one. So is A giving you this number? Can A give you 7.4 or not? If A is 7.5 minus 1 becomes, let's say 8, 6.5, right? If it's plus 1 becomes 8.5. Is 7.45 larger than 6.5, smaller than 8.5? Yes. So A is correct, right? So now let's say B. B is 3.74. So 3.74 minus 1 is what? 2.74. So 3.4 plus 1 is 4.74. Is 7.45 in this range? No, it's larger than both of them, right? So B is not right because 7.4 is larger than both of them. Doesn't meet my requirement. I need larger than this number and smaller than this number. Now let's just say 1.95 minus 1. Say 1.95 minus 1 is 0.95. And 1.95 plus 1, 2.95. So is 7.45 smaller than any number? No, it's larger than both. So it doesn't meet my requirement. It must be larger, smaller, the same time meet. Okay? So now D, same thing as B, right? So 3.34 minus 1 is 2.34. And 3.34 plus 1 is 4.34. But I need my 7.5 larger than this, smaller than this. So it doesn't satisfy, right? So here 7.45 even smaller than the pKa plus 1. So I cannot pick that one. So A is your only choice. Okay? A is the only choice. It meets your requirement. So that is how to solve this problem. Okay? So you're given pH, you say which pKa can satisfy your requirement, can meet your requirement. Okay? So now, get some idea? So now let's say number 4, try to work by yourself.
She pretty much just put it in that little inequality. She just like, it's easy. It is. It's being active.
Same method, right? So think about that. Maybe 1 minute.
That's actually really it's bothering me. I don't know how to work. Take it out. Break me up. It's stressful. It's kind of close and it feels into your bones. It feels into your bones. Or working out? Yeah. I'm good on this game, though. If you're taking it wrong, this is easy shit. And you want to speed up, man. That's really so polite. Stings sometimes. That's why they get a full answer. Is it C or D?
Anyone get the answer? Which one? C, right? Okay, good. You guys get good answer. C. Why is that? Still the same way test. First you need to know to make a good buffer, pH range should be this. pKa minus 1, pKa plus 1. So okay. So let's say 1 by 1. A, when your pKa plus 1, 5.19. When your pKa minus 1 first. Minus 1, 3.19.
That's 4 points.
And the pKa plus 1 is 5.19. What I need is 8.10 just in between of these two. And now my 8.0 larger than both, right? So it doesn't meet my requirement. So B, pKa minus 1 is 2.46. pKa plus 1 is 4.46. My pKa, I need 8.1, so still larger than this. Let's say 7.84, so 7.54, minus 1, 6, plus 1, 8. So my pH 8.0. It is larger and smaller than this.
Beautiful.
So meet my requirement. And then you have D, let's say. Minus 1, 8.31. It's very easy to, some people mispick D. So 8.31 plus 1 is 10.31. But my pH, I need 8.1, so it's smaller than both, right? So it's smaller than both. Still doesn't meet my requirement. So E, even smaller. So of course not, right? 0.09 and then 2.96, far away from my buffer requirement. So that's it. So as long as you know this range, so you should be fine with this problem. But therefore, you may get a question in your test instead of telling you the pKa. If you're given all the Kas, so what do? Yeah, you get an extra step, right? You need to find the pKa first. If you're not given pKa, you're just given Ka, right? But here you're already given Ka. Okay, alright? Just be careful for that. So any questions, comments about this two formula? Okay, so just a example for the PhD. Alright, so now continue with pH and pKa and the buffer, right? So we talk about, yes.
From the bottom.
You said if you weren't getting PKA, but just getting PKA, you said there'd be an extra step.
So extra step is you need to calculate pKa.
How would you?
You don't know?
Could you tell us that?
Again, anyone know how to convert Ka to be pKa? What is P mean? Negative log. So pKa equal to negative log Ka. Okay? So if you forgot, because I remind you here, right? pKa equal to negative log Ka.
You don't know.
Again, pKb equal to negative log Ka. Right? So now, formulas. Any other questions? Titration, right? So titration basically is the application for the relationship between pH and pKa. So after today, you're going to figure out, you're going to understand why can we use titration to determine pKa when I was doing experiment in 1211. At that time, probably you don't know, right? So why pKa can be determined through pH. Measuring pH, you use pH meter, measure pH, and eventually you determine the pKa. So how could that happen? Right? So because you have the Harrison-Hausberg equation, it tells you the relationship between pH and pKa. Right? So when we do titration, I believe you should be familiar with this curve, right? So the last experiment, everybody should get this type of curve. You were told you need to get a jumping point. You will say pH jumped a lot, right? In certain point. If you miss that point, you need to redo your experiment. So now let's see what is that point. Why that jumping point is so important. So when you do titrations, two possibilities. In 1211, we always use a base to titrate an acid. Sometimes hydrochloric acid, sometimes KHP, so they are all acid, right? Strong acid and weak acid. But you're using a base to titrate your acid. So then you keep adding base. In the beginning, you have a lot of acid, so your pH is lower than 7. So you keep adding base, eventually you get a lot of base here, right? So you got your pH, it's about 12, or even higher, maybe 14, right? So higher. And in between, equivalence, we call it a equivalence point. This point is very important. That's your jumping point when you have a titration experiment. So exactly what is equivalence point? So equivalence point, first let me give you the definition, right? Is when your amount of acid equal to your amount of base. So when we say amount in chemistry, we say moles, right? It's the moles of acid equal to moles of base. Okay? So it's the amount. And another possibility. So now you're doing 12 lab, right? You know you can not only use a base titrate acid, but you can also use a acid titrate a base. Okay? When you use the acid titrate a base, initially you get high pH, still 12, and then eventually you get a low pH. two possibilities for titration, and no matter which one, you're going to reach a ending point, or we call it an equivalence point. And a very important property for equivalence point, moles equal to moles. And that is a foundation, or that is all the theory behind the titration, how you determine the ending point. Okay, when you reach the point, amount of acid equal to amount of base. Be careful again, it's the amount, okay, moles. Also, some people may think, so what is the pH at the equivalence point? Most people will say 7, because your moles of acid are already equal to your moles of base. The answer is not really. It can be 7, it can be less than 7, it can be larger than 7. Depends on the strength of your acid and base. Yes, if you have strong acid titrate with strong base, pH at the equivalence point always 7. Only if you have strong acid titrate strong base, or strong base titrate strong acid, you get eventually your salt is neutral, right? So when you reach equivalence point, it's 7. But if you have a weak acid, let's say you have a weak acid titrate with a strong base. For example, you do KHP, right? In 1211 you do KHP titrate with sodium hydroxide. So when you reach equivalence point, the salt is made of a strong base and a weak acid. So what kind of acid is acidic or basic? It's basic, strong and weak, right? So you get pH larger than 7. Okay, if you have a weak acid, strong base. But if you have a strong acid, weak base, then when you reach equivalence point, what will happen? Strong one will win, so you get the acidic solution. For example, in 1212, you did the hydrochloric acid titrate with sap. Right? When you reach equivalence point, your pH actually is less than 7. So we cannot use pH to determine the equivalence point. Instead, you can only use the amount. Okay? Amount. And if you get a true or false question, right, a statement in your test to say, okay, when you reach your titration, when you reach equivalence point, the pH should always be 7. That's wrong, because you don't know what kind of acid, what kind of base. All these possibilities will exist. Okay? So clear about the titration ending point. Sometimes it calls ending point. But the formal name should be equivalence point. Okay? Equivalence point. So now, let me ask you, since we say when you reach equivalence point, you have this amount equal to each other. How about before you reach equivalence point? Let's say this area. That is before you reach equilibrium. So what happens is your acid base exists at the same time. When the acid and base exist at the same time, this area can be treated as your buffer system. Before you reach equivalence point, it's a buffer area. Before you reach equilibrium, this is your buffer. Okay? Keep in mind that. So here, before you reach equivalence point, solution can be treated as a buffer. And of course, I mean, if you have anything is weak. If you have this strong thing, there is no buffer, right? But if you have anything weak, so you have a buffer. So here, let's add the origin equivalence point. If you have anything weak, right? You have weak acid or weak Only if you have anything weak, this can be treated as a buffer. And since it's a buffer, right? Since this is a buffer, we got an important conclusion here. Let me give you the conclusion, and then we will give you example, explain why. So pH equal to pKa at half equivalence point. pH equal to pK. Again, since you have pKa, that means you got anything weak, right? Only for weak acid or base, we talk about pKa. Okay? So at half equivalence point, you have pH equal to pKa. Yes. So equivalence point is here, for example, right? So you get volume. So half equivalence point would be here. Okay, so half. For example, here is weight. So VEQ, here will be half VEQ. Alright? Good question. So at half equivalence point, halfway. So your pH equal to pKa. Let's say why is that? So now let's say, why is half? Say an example, then more sense. Okay, so you're given 40 milliliter of this concentration of nitrous acid. Is a weak acid or strong? It's a weak, right? Because NO3 is strong, NO2 is weak. And titrate with a strong base. Calculate the volume of potassium hydroxide required to reach equivalence point. What happened at the equivalence point? The amount? Okay, at the equivalence point, moles or amount, right, of acid equal to moles of base. That is how we define this equivalence point. Equivalence means moles equivalence, okay, amount equivalence. So that means my moles of nitrous acid should equal to moles of base, potassium hydroxide. So how many moles of acid do I have? Can you calculate? Yes, right? I got 40 milliliter and I got 21 mole per liter. So I need to first convert 40 milliliter to be 0.04 liter. Is that correct? Divided by 1,000, right? 0.04 liter. So now I'm going to calculate mole of acid, 0.04 liter times 0.1. Molarity means mole per liter, right? So your liter cancelled, so you only get moles, right? So that is my moles of acid, 0.004 mole of acid. Any question here? You're given molarity, you're given volume, so you can calculate how many moles you have, right? So based on the definition for molarity. Right? So that is moles of acid. So for the base, you only given concentration, but because of this, so my mole of, so mole of potassium hydroxide should equal to mole of acid, equal to 0.004. Okay? Okay, so now you know moles of your potassium hydroxide and you're given concentration. Can you calculate the volume? Yes, right? So because molarity equal to mole over liter. So your liter, I don't know, right? Liter should equal to mole over molarity. So then it should equal to 0.004 over 0.2. Well, you got 0.02 liter. Don't forget the liter. It's your unit. So 0.02 liter equal to 20 milliliter. Right? Times 1,000. The reason I convert to milliliter just keep constant. Right? If you have a question in your test, depend on your choices. If they are all in liter, you pick liter. If they are all in milliliter, you convert it to milliliter. So that is for it. So you solve it. And again, this math is not that hard. But the key point is you have to understand what happened at the equivalence point. More acid equals more of this. Okay? Any question for the first asking? Now let's say B. B is asking you the pH after adding 50 milliliter of. So you're doing titration, right? So when you do titration, the potassium hydroxide is not like immediately added. In your burette, you're doing drop by drop, right? So in the beginning, you're not adding all your potassiums. For example, totally you need 20 to reach your ending point. But in the beginning, there is a point you only use the 5. Here's your ending point. Or equivalence. So before you reach equivalence point, what did I tell you?
Buffer.
It's a buffer, right? Because you have a weak acid there.
Yeah.
Okay? So if it's a buffer, how to calculate pH? Addison Haskell equation. Concentration of base. So what is the base here? Very easy to use potassium hydroxide, but it's a strong. So our buffer should not have strong. So what is your base here should be? Conjugate base from your weak acid. Okay? Should be the conjugate base from your weak acid. So what happened, how to get this conjugate base, right, is because when you add this potassium hydroxide, you have this reaction. So this reaction is a one direction reaction. Okay? So you have water, and you have this. Before you reach any point, most contents in your buffer system is your weak acid. So this weak acid mixed with this conjugate base, they form a buffer, right? So this form a buffer. Okay, this form a buffer. So now, let's say what happened in this reaction. Now let me write down this. What happened to this reaction? In the beginning, you have the concentration is 0.1. So So we already know the moles, right? 0.004 moles. That is the initial beginning. Then you add 5 milliliters, so you don't have any this, 0, right? So you add 5 milliliter of potassium hydroxide, 5 milliliter. Okay, convert it to be liter and times the concentration. What you get is 0.001. That is what you add. You add this amount of potassium hydroxide. When you add this, so the acid will react with this base, right? So then you going to react 0.001. Because you add the base will react with the acid, right? You add 0.001 potassium hydroxide, we discussed this before, remember how to determine the pH change when you add a small amount of potassium hydroxide, right? So here 0.001 is what you add. And then when you have this reaction, there is the salt will be formed. Okay, the salt will be formed. So after reaction, this is not an ice chart. After the reaction, initially you get 0.004. So now you have 0.003 because you use the 0.001. And for the base, you get conjugate base, 0.1, which is produced through this reaction. And now this, after reaction, the leftovers of this acid with the new formed conjugate base. These two will form a buffer, right? So then your pH equal to pKa plus log concentration of your conjugate base 0.001 and the concentration of your acid 0.003 because they are in the same container, right? So the volume is the same, so I can just use the moles. Okay? So then you solve your pH. So pKa is given in the question 3.34 plus log 1/3, right? So you get pH eventually I got 2.86. Okay, so that is what happened when you only add 5 milliliters of potassium hydroxide. So you have to understand the new buffer system. And then how to determine the concentration? A little bit tricky here, right? So eventually all this potassium hydroxide is gone. But you still get some acid left. This left acid form a buffer with salt. Okay? So just quickly finish say CH at 1/2 of the equivalence point. CH equal to pK. That's it. Yes.